This video is on hyperbolic functions, and this is our last video for the semester, and you guys have done a great job, so hang in there. We're almost done. Hyperbolic functions, I messed that up. Okay. Hyperbolic functions are they're combinations of these two functions, these exponential functions, that are used very frequently, and they're used so frequently that they're given special names. So it's e to the x and e to the negative x. It's combinations of these two functions. They have the same relationship to a hyperbola that trig functions have to the circle. So if you recall trig functions, sine, cosine, tangent, secant, cosecant, secant, cosecant, and cotangent, those relate to the circle, and these hyperbolic functions relate to a hyperbola. There are many similarities between hyperbolic functions and trig functions. Trigonometric functions. And so for that reason, they got named hyperbolic sine, hyperbolic cosine. They got named with a trig name because there's so many similarities. We're about to define some of these. So the hyperbolic sine, this is how you write it. S-I-N-H of x. The hyperbolic cosine, C-O-S-H-X, and so on. The hyperbolic tangent, cosecant, secant, hyperbolic cotangent. You just slip a little h in there, but this is the symbol, symbolically. The sine, the hyperbolic sine, is defined to be e to the x minus e to the negative x divided by 2. It's the combination of e to the x over 2 minus e to the negative x over 2. Cosine is the combination of e to the x plus e to the negative x divided by 2. Tangent, we can write it in terms of the exponential functions, but it is the sine, the hyperbolic sine divided by the hyperbolic cosine. Cosecant is 1 over the hyperbolic sine. My dog has gotten a hold of some plastic and is having a big time. That's the noise you hear in the back. Secant is 1 over the hyperbolic cosine, and cotangent is the hyperbolic cosine over hyperbolic sine, just like you have seen before. There are identities for the hyperbolic functions that are analogous to the trig identities. They are not exactly the same, but if you'll recall in trig, the Pythagorean identities, here is 1 sine squared of x plus cosine squared of x is equal to 1. This is one of the Pythagorean identities. Well, there is a hyperbolic identity that says cosine squared, hyperbolic cosine squared minus hyperbolic sine squared is 1. And I put that little squared in the wrong place, so let me correct that. It goes after the h, so that is how they would write that. Also, there are addition of two angle identities for sine and cosine and tangent. So if we took like the addition sine of x plus y, the addition of two angles, this is sine cos plus cos sine. If you recall seeing this identity, they have other ones for hyperbolic sine. For instance, hyperbolic sine of x plus y is the hyperbolic sine of x, the hyperbolic sine cosine plus hyperbolic cosine, hyperbolic sine. Now, oh, that's supposed to be y. So, oh my goodness, I put x's on all these. I meant to put x, y, x, y. Okay, so these ended up being the same, but they're not all the same. So when you get into this, and you will see these again, and if you look at the in section 3.11, you can see all of the identities. I just wanted to mention that there are similar. They have identities for the hyperbolic functions just like they do for sine, and so they're not exactly the same. You see how this has got a minus and this is a plus, but they do have identities there. Okay, so let's look at the graphs of hyperbolic sine. It is the combination of e to the x over 2 minus e to the negative x over 2. So if we were to graph e to the x over 2, it is going to look like an exponential function. It's going to do this. It's going to hug this, and it's going to kind of go up here like this. This would be 1/2 e to the x. And then negative 1/2 e to the negative x. If we take this, if we say minus e to the negative x over 2, or we treat that as negative 1/2 times e to the negative x, there are some reflections involved across the x and across the y, and it would end up looking like this. That's what this one would look like, minus 1/2 e to the negative x. And so the combination, the addition of these two functions would look like this, basically. What this would look like. So I'm about to highlight what the hyperbolic sine looks like. Sort of comes in here like this. It's gonna sort of look like that. Okay. The domain for this guy is all reals. And the range is also all reals. Okay, let's have a look at the cosine. The cosine is e to the x divided by 2, or 1/2 e to the x, which still looks the same. It's this right here. Okay, and then we're going to add 1/2 e to the negative x, which just has a reflection across the y. So that's what this looks like this. And if we add these two functions together, so this one was e to the x over 2. And this one is e to the negative x over 2, or 1/2, however you want to think of that. So the combination of these two is, if this is on the y-axis, this is a 1 on the y, we get this parabola shape here. So let me highlight what the hyperbolic cosine looks like. Looks like that. We can see that his domain is all reals, negative infinity to infinity, and the range is different. The lowest it hits is 1, and then it goes up to infinity. That's his range. All right, let's have a look at the hyperbolic tangent. This is the hyperbolic cosine divided by hyperbolic sine divided by hyperbolic cosine. And so this guy has some asymptotes. They have horizontal asymptotes. Horizontal. And so there's one at y is 1, and there's another one at y is negative 1. And so if we call this as y is 1, here's a horizontal asymptote. Here's another one, y is negative 1. Y is negative 1. Then it sort of takes almost like a cube root of x look. Only it's got these asymptotes. It doesn't continue to decrease. It gets trapped in there. It kind of hugs that. I guess I could make this go on a little bit so you can see how it hugs this line. So this is what the hyperbolic tangent looks like. His domain is negative infinity to positive infinity, and his range is parentheses negative 1 to 1. It doesn't cross the asymptote. Okay. You're going to see mathematical uses of hyperbolic functions in Calc 2. The applications of these functions in science and engineering occur whenever light or velocity or electricity is gradually absorbed or extinguished. One major application of the hyperbolic cosine is that it is used to describe the shape of a hanging wire. Like if you've ever seen electrical wire hanging or telephone wires hanging, then that function describes the shape that hanging wires make, and so they can model things off of that. Okay, let's just look at the derivatives, just like sine, cosine, tangent. The trig functions have derivatives. So do the hyperbolic trig functions. Let's see, just like trig functions have inverses, hyperbolic functions have inverse, like inverse sine, inverse cosine. They have inverse hyperbolic sine, inverse hyperbolic cosine, and so on. So those are similar. What I've chosen to do is just to look at with you guys the derivatives of the hyperbolic functions, not go into the derivatives of the inverses and all of that. So I have them printed here. And so all we're going to do is practice taking derivatives. This will not be anything new, really. It's applications of a new function, but the same type of derivatives that you are already good at doing. So let's just have at it. Let's take the derivative of the hyperbolic tangent. And so we'll just look here and get used to what it is. The derivative of the hyperbolic tangent is secant squared. So if we need to find the derivative, f prime of x, this is going to be secant squared, hyperbolic secant squared of, not of x, but of 3x, because that's what the inner function was, times the derivative of the inner function. So we still have to use chain rule, so this will be times 3. So if I clean this up a bit, it's going to be 3 hyperbolic secant squared of 3x, and that is going to be our derivative right there. H of x is equal to the hyperbolic cosine of x to the fourth. So we'd say h prime of x will simply be the derivative of hyperbolic cosine, which is sine. So you see how there's not, in trig functions there's a negative there, but in this hyperbolic function there's not. So the derivative of hyperbolic cosine is hyperbolic sine, so it's going to be sine h, not of x, but of x to the fourth, because that was what our inner function was, times the derivative of the inner function times 4x cubed, power rule. So 4x cubed times the hyperbolic sine of x to the fourth, if I clean that up a little bit, is the answer. All right, let's look at g of x. This is going to be power rule. We have two functions of x being multiplied, so g prime of x will be first times the derivative of the second. So the derivative of secant x is negative hyperbolic secant times hyperbolic tangent. So that is first times the derivative of the second plus second hyperbolic secant times derivative of the first, 2x. And so I'm just going to write it a little bit cleaner. Negative x squared times hyperbolic secant hyperbolic tangent plus 2x times hyperbolic secant. All right. Then h of t is equal to the tangent of e to the x. So you just say, okay, outer function is hyperbolic tangent, inner function is e to the t, so it's some chain rule. H prime of t is going to be secant, hyperbolic secant squared, secant h squared of e to the t times derivative of the inner function, which is just e to the t. So I like to write it in this order so nothing looks like it's an argument. All right, that's that derivative. So you can see this is very much like what we've done before. Look at number 5. That is a crazy looking function. We have to do the same thing that we did before when we encounter something exponential like this. We use logarithms to help us do this. So this calls for logarithmic differentiation. So what I'm going to do is take the natural log of both sides. The natural log of y is equal to the natural log of x times the hyperbolic cosine of x. And now I'm going to use, since I've introduced the logarithm, I get to use the log laws, which says put the power in front if I want to do that, and I do. The natural log of y is equal to hyperbolic cosine times the natural log of x. And so now I'm going to finally take a derivative. Take the derivative of both sides. Goes like this. The derivative of the natural log of x is 1 over y, but y is a function of x, so we have some chain rule times y prime, is equal to, this is going to be product rule. First, hyperbolic cosine of x times the derivative of the second, 1 over x, plus second, natural log of x, times the derivative of the first, which will be hyperbolic sine of x. And so now I want to solve for y prime, so I multiply both sides by y. So y prime is going to be the hyperbolic cosine of x over x plus sine, hyperbolic sine times natural log of x. I didn't have to switch that order, I just did for some reason. Times y, and y is equal to x raised to the hyperbolic cosine of x. All right, that is the answer to this guy. Last one, number 6. This is product rule. We have a function of x, which is x, times another function of x, which is the log of the hyperbolic secant of 4x. And so it goes like this. Y prime will be first times the derivative of the second. So that's going to be times 1 over secant, hyperbolic secant of 4x. Oh my goodness. Times, this is a lot of chain rule going on, times the derivative of hyperbolic secant, which is negative secant, hyperbolic secant of 4x, times hyperbolic tangent of 4x, times finally the derivative of the most inner function, which is 4x, times 4. So I'm just going to put times 4 right there. Okay, first times the derivative of that, plus second the natural log of the hyperbolic secant of 4x times the derivative of the first, which is just a 1. We can clean this up a little bit. Will look like this. I have the secant of hyperbolic secant of 4x over the hyperbolic secant of 4x, which can be divided out. I have a negative 4x times the hyperbolic tangent of 4x plus the natural log of the secant of 4x, the hyperbolic secant, whoops, there's my little h, of 4x. Yep, that's it. All right, that is just a brief look at hyperbolic functions.